Something truly remarkable happened in space, something that scientists are still struggling to fully understand. NASA's Hubble Space Telescope, which has given us countless glimpses into the depths of our universe, captured this astonishing event, but not because it was planned. It wasn't on anyone's radar. The telescope wasn't even supposed to be looking in the direction where the event unfolded. It was supposed to be focused on a completely different comet. But fate, or perhaps something more, intervened. This cosmic anomaly was not just any comet passing through our solar system. It wasn't a routine visitor on its orbit around the Sun. This comet did something extraordinary. It shattered, but not in the way we typically understand a comet, to disintegrate over time. This comet came apart in real time, its fragments breaking off in front of our eyes. And what's even more perplexing is that the telescope that was meant to look elsewhere ended up capturing this comet's destruction entirely by accident. What followed was a story that would send ripples throughout the scientific community and raise questions that remain unanswered. Months after the data was collected, after scientists had pored over the images, and after a peer-reviewed paper was quietly published, something strange was revealed. The comet didn't just get close to the Sun, it tore itself apart, piece by piece, in a dramatic spectacle that was captured right as it was happening. This was an event so rare that it was only the second time in history anyone had observed such a thing happening to a comet in real time. It was an unexpected discovery that raised alarms, opened new mysteries, and left a flood of unanswered questions. If you've been following the recent stream of anomalies in our solar system, or if you've heard the name Atlas thrown around in scientific circles recently, you'll know that things are not always as they seem. In fact, if you've been paying attention to the stream of unusual findings that have been occurring in the past year, this event is not an isolated incident. It's part of a larger puzzle that is beginning to form. If you're still here, buckle up, because what I'm about to explain connects more dots than you might expect. Before we dive deeper, make sure to hit that subscribe button. Trust me, you won't want to miss what's coming next. Hit the like button if you're ready to uncover the truth about this bizarre space event. Because what I'm about to walk you through is the kind of story that tends to get buried in technical jargon and academic papers. But don't worry, I'm going to make sure you understand every single piece of it. Let's start with the facts we know for sure. On November 8th, 2025, the Hubble Space Telescope pointed its high-powered lens at a comet named C 2025, K1 referred to as K1 for short. Sounds simple enough, right? The team was supposed to take a 20-second exposure, capturing one image of the comet. Then, on the following days, November 9th and November 10th, the team took two more 20-second exposures. 3 images, each one capturing a comet's movement across the sky. It was routine, or at least it seemed that way. But when John Nan, one of the lead researchers, checked the images the morning after the first shot was taken, he was stunned. What he saw made him stop in his tracks. There weren't just 2 or 3 comets in the frame. No, there were 4. 4 separate comet-like objects in the image. That wasn't supposed to happen. The team had expected only one object in the frame, but instead, there were 4 distinct comet-like bodies. Each of these bodies had its own glowing coma, the bright halo of gas and dust that surrounds a comet as it gets close to the Sun. Now, as you might imagine, seeing 4 comets in one image isn't exactly a common occurrence. By the second day of observations, the largest fragment in the frame, the one that had been visible from the start, had split again. And by the third day, the fragments were no longer just a few pieces. They had spread out farther and farther along a diagonal path across the frame. Now, let's pause for a moment and think about how extraordinary this actually was. K1 wasn't just another comet. passing through our solar system like we see every year. No, this comet wasn't simply brushing past the sun, it was falling apart right before our eyes, and Hubble was the only instrument in the world sharp enough to catch it in real time. This event unfolded in a way that had never been seen before, and it wasn't just the fragmentation that was rare. The timing? Well, that's where the real mystery lies. Here's the real kicker. This whole thing shouldn't have even happened in the first place. Hubble wasn't supposed to be looking at K1. The team had originally planned to study a completely different comet, but then something unexpected happened. The original target, the comet they had prepared for, suddenly became unavailable. What does that mean? A sudden technical constraint. That's what. A glitch, a shift in the system, or perhaps something else entirely, something that made their intended target no longer visible to Hubble. In a scramble to fill the gap, the team was left searching for a replacement, and that's when they found K1. Within 24 hours of that first observation, the comet was already in the process of breaking apart. Can you believe the odds of this? The team was meant to study one comet, and through a twist of fate, they ended up witnessing a comet on the verge of catastrophic fragmentation. It wasn't just a coincidence, it was a scientific marvel that could only be caught by a telescope like Hubble. So, how did they figure out when the fragmentation actually started? That's where Hubble's unparalleled resolution comes into play. Using the sharpest lenses available, scientists were able to track each fragment's movement and even trace them backward in time. They discovered that the comet had begun to fragment about 8 days before Hubble's first image on November 8th. So, on October 31st, 2025, Halloween, K1, a comet roughly 5 miles wide, began to break apart. This wasn't just a small comet either. For comparison, a 5-mile wide comet is larger than most, making K1 a significant object in our solar system, and yet we almost missed it entirely. At this point, we have to take a moment to consider how extraordinary this comet's journey really was. K1 had already passed perilously close to the Sun, much closer than any of us expected. Its perihelion, the closest point in its orbit around the Sun, occurred about a month before the Hubble observations. K1 came within Mercury's orbit, passing a mere 1/3 of the distance between Earth and the Sunday. Imagine the temperatures over 800 degrees Fahrenheit. The gravitational forces alone should have torn the comet apart long before it reached such an intense proximity to the Sunday. But K1 held together barely. It survived the perilous heat, the extreme tidal forces, and the gravitational stress. Then, just days later, it began to fragment. The real question is why? Why did it take so long for the comet to break apart? Why did it endure the intense heat only to shatter days later when it should have been long gone? Scientists have a theory. K1's internal collapse was delayed. After surviving the brutal conditions of its perihelion, the comet managed to hold itself together through the worst of the stress. But once it had passed the Sun, the temperature differential between the sun-facing side and the shadowed side of the comet caused the final collapse. The Sun's heat might have cracked the surface, but it wasn't until the temperature difference between the two sides reached its breaking point that the comet finally gave way. The pressure inside built up and exploded, sending fragments of the comet scattering outward. This delayed collapse, a slow unraveling of the comet's structure, isn't something we normally see. But in this case, it was almost as if K1 had survived the worst, only to fall apart once it was in the cooler darkness of space again. It's a fascinating phenomenon, and yet it doesn't completely explain everything we saw next. When a comet's nucleus cracks open, scientists expect certain things to happen. The exposed interior of the comet should release ancient ices, water ice, carbon dioxide ice, and organic compounds that have been frozen for billions of years. The moment these ices are exposed to sunlight, they should sublimate, turning directly into gas. This process creates the comet's tail, a bright, visible stream of gas and dust that we associate with comets. But when K1 fragmented, something completely unexpected occurred. Instead of the usual dramatic, bright outburst of gas and dust, there was nothing. Or rather, there was a delay, a prolonged silence. The comet broke apart, but the ice didn't sublimate immediately. This didn't fit with anything we've observed in comet fragmentation before. The expected surge of brightness, the comet tail, didn't appear instantly. There was no immediate outburst of gas, no brightening of the comet's coma. It just didn't happen. At first, scientists thought it might just be a minor delay in the expected sublimation process. After all, comets are strange, and sometimes they don't behave as predicted. But after further analysis, the anomaly deepened. Ground-based telescopes were tracking K1 during this time, and they reported the same strange phenomenon. K1 didn't respond the way it should have. The comet's fragmentation didn't produce the expected visual effects. The normal reaction, an explosion of gas and dust, was nowhere to be seen. The researchers proposed a few possible explanations. One theory suggests that a thin layer of dark, desiccated dust might have formed over the exposed ice, preventing sublimation from occurring immediately. Essentially, the ice was covered by a protective layer that delayed the outburst. Another possibility is that the comet's subsurface heat needed time to build up enough pressure before it could expel a shell of dust outward. These theories are reasonable, but they still leave a larger question unanswered. What does this tell us about the comet's internal structure? K1 wasn't just a simple, homogeneous ball of ice. The fact that it had these complex layers, an outer shell of processed dust and an inner core of ancient material, suggests that K1's interior was far more complex than originally thought. This discovery is a monumental step in our understanding of comets. It tells us that K1 wasn't just a simple leftover from the formation of the solar system. It had been shaped over time, processed, and altered, and its ice wasn't as pristine as we believed. When K1 cracked open, we got a glimpse into the material that had remained hidden for billions of years, untouched by sunlight. And now, that ancient material is being scattered across the cosmos. But the oddities don't end there. As the data from Hubble continued to pour in, the most shocking revelation came. K1 was carbon-depleted. This is something scientists didn't expect in the slightest. You see, every comet we've ever studied, from Halley's Comet to Hale-Bopp and beyond, has had one thing in common: carbon. Carbon is one of the most abundant elements in the universe. It's the building block of life and the foundation of organic chemistry. If there's one thing you can count on in a comet, it's carbon. But with K1, something was off. The carbon content was significantly lower than expected, so low that it made scientists question their own data. The readings were so strange that the research team double-checked their instruments. The carbon depletion was not something that could be easily explained. It was an anomaly, one that scientists couldn't fit into their existing models of comet composition. This carbon depletion isn't just a minor blip in the data. It's a fundamental difference that could change how we understand comets and their origins. Carbon is always there in comets, so the absence of it in K1 raised immediate red flags. The spectroscopic data collected by Hubble was still being processed, but even in its early stages, it was clear that K1 was unlike any comet we've studied before. So, what does this mean? Well, It could mean that K1 didn't come from the same region of the solar system as other comets. It's possible that its composition, its missing carbon, could point to a completely different origin, one that doesn't align with the rest of the solar system's formation. It could also suggest that K1 had been altered, processed, or changed over the course of its long journey. Now, here's where things get even more intriguing. K1's full designation is C 2025 K1 Atlas. The Atlas part is important because it refers to the asteroid and comet survey system that discovered K1. If that name sounds familiar, it's because you've probably heard of Atlas in connection with another mysterious object, 3I Atlas, the interstellar object that passed through our solar system not long ago. The same system that detected K1 also discovered 3I Atlas, an object that has been the subject of intense scientific scrutiny for months. But here's where it gets really interesting. K1 and 3I Atlas are not the same object despite some surface-level similarities. Both were discovered by the Atlas survey, and both have displayed anomalies that challenge our understanding of comet behavior. Could these two objects be connected in some way? While no one in the scientific community has explicitly linked them, the fact that both were discovered by the same survey system during the same time frame raises questions that need to be answered. K1 is now 250 million miles from Earth, and it's drifting toward the constellation Pisces. Its trajectory is taking it out of the solar system, and scientists are now saying that it's unlikely to ever return. The fragments are continuing to spread outward, and the ice is slowly sublimating. But the real mystery is what K1's composition could reveal about the very origins of our solar system. And unfortunately, that opportunity is quickly slipping away. The comet is fading, its fragments growing weaker and farther apart as they travel. The data that has been collected is still being analyzed, and the full chemical portrait of K1's interior is still being processed. But one thing is clear. K1's fragmentation, its missing carbon, and its delayed sublimation are telling us something new, something that could change how we understand the solar system's formation and the very nature of comets themselves. The story of K1, as extraordinary as it is nearing its end. The comet has traveled 250 million miles from Earth and is now in the constellation Pisces. It's heading outward, far from the sun, and its trajectory suggests it's unlikely to ever return to our solar system. The fragments that broke off are now spreading into the vast emptiness of space. The comet's ice is sublimating, turning into gas and dust, and the ancient materials it carried within its core are dispersing into the void. As each day passes, the comet grows fainter, the signals weaker. The opportunity to observe and study K1 with high-resolution instruments has already closed. What remains is what Hubble captured in those few precious frames, along with the spectroscopic readings taken in the weeks following. In the months since, the scientific community has been processing the data, trying to understand what it means, why K1 was so different from every other comet, and what it can teach us about the early solar system. A paper was published in March 2026, titled Sequential Fragmentation of C 2025 K1 Atlas after its near-sun passage. The team describes how K1 didn't just break apart all at once. It fragmented in stages, like a structure failing from the inside out. First, the main nucleus cracked. Then, one of the smaller fragments split again. These stages were mapped precisely by the team, giving scientists a rare, detailed look at how a comet disintegrates. But that's just the surface. The deeper mystery lies in the composition of K1 itself. As we've learned, comets are often considered the ancient building blocks of our solar system, frozen relics that carry a record of the early days of our cosmic neighborhood. When K1 cracked open, it revealed something unexpected. The comet's interior was not what scientists had anticipated. It was missing something crucial: carbon. This carbon depletion isn't a small detail, it's a significant anomaly that raises questions about where K1 came from and what it was made of. And here's where things start to get even more complex. The fact that K1 was discovered by the Atlas survey system, the same system that flagged 3I, Atlas, adds another layer to this puzzle. Could there be a connection between the two objects? At this point, scientists haven't proposed one publicly, but the coincidence is hard to ignore. Both were discovered by the same survey system during the same period, and both have shown characteristics that defy our understanding. Could this pattern be a coincidence, or is something else at play here? As we move forward, the window for further study is quickly closing. K1 is drifting farther into space, and the opportunity to study it at close range is slipping away. The data collected by Hubble, those three critical frames, will be the cornerstone of our understanding of K1. But the spectroscopic readings, which could reveal even more about the comet's chemistry, are still being processed. There's still so much we don't know. This is where things get truly fascinating. When scientists say that the spectroscopic analysis of K1 is likely to reveal much more about the composition of K1 and the very origins of our solar system, they are not speaking lightly. These are not the kinds of words scientists use for mundane results. This is a hint that what we're seeing in K1 could force us to revise some of our most basic assumptions about the solar system and its formation. K1 is offering us a glimpse into a past we can't fully see. Its strange behavior, its missing carbon, its delayed sublimation, they all suggest that this comet came from somewhere different, something we've never been able to observe directly. And here's the kicker: K1 came from the outermost regions of our solar system, areas we've never truly explored. We've sent probes to Pluto. We've photographed galaxies billions of light years away. But that distant region where K1 originated, we've never seen it up close. We infer its existence only from the objects it sends, inward objects like K1. And now, K1's chemistry, its strange carbon depletion, and its fragmented state are scattering into space, taking with it the secrets of that distant region. K1 may be gone, but the questions it left behind are far from over. The scientific community is still grappling with what this comet's strange behavior means for our understanding of the solar system. What K1's disappearance leaves us with is a series of questions, ones that are likely to shape the future of comet research for years to come. As the final fragments of K1 drift into the darkness, the opportunity to fully understand this comet's origin and composition has nearly passed. But the questions it raised, the anomalies it displayed, and the strange timeline of events will linger, waiting for the answers that could fundamentally change how we view the origins of our solar system. So, as we wait for the final spectroscopic data to be revealed, we are left with one thought. K1 might be gone, but the story of what it left behind is far from over. If you've been captivated by this unfolding mystery, make sure to hit that subscribe button and leave a like. These kinds of discoveries don't come along often, and when they do, it's important to be the first to know what's happening. If something in this story left you with a burning question or an idea you can't shake, drop it in the comments below. The questions K1 left behind might just be the most important ones that have yet to be asked.